Let us look at Euclid's division lemma. Recall that the dividend is equal to divisor times quotient plus remainder. The remainder has to be less than the divisor. Now we could rewrite this as A is equal to BQ plus R, where R is less than B but greater than or equal to 0. Now this is known as the Euclid's division lemma. Now this algorithm is used for finding the highest common factor between two numbers, and it is also used for finding properties of numbers. Let us see how. So we guess B and we determine various values of R and eliminate cases. Let us see a few examples. Show that every positive even integer is of the form 2q and that every positive odd integer is of the form 2q plus 1, where q is some integer. So let us write down our Euclid's division lemma as A is equal to BQ plus R, where A is a positive integer. Now let us reread our question. We are talking about 2q and 2q plus 1. So let us take B as 2. So R is going to be less than 2 and greater than or equal to 0. Now let us write down our cases. Either R is 0 or R is 1. So we have two cases. In the first case, we see that A is equal to 2 times Q, which means that it is divisible by 2. So A is equal to 2Q would be an even integer. Now since we either have even integers or odd integers, so the integers that are not even shall be odd. Here 2Q plus 1 would represent odd integers then. So we are applying simple logic here. If 2q is even, then 2q plus 1 has to be odd. Now we are talking about positive integers, which means that 2q has to be greater than or equal to 0, or q has to be greater than or equal to 0. Let us look at another problem. Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. Let us write down Euclid's division lemma once again. Now here we are talking about 6q. So let us guess B as 6, or let us take B as 6. Now R has to be less than 6. So we shall get 6 cases where R has values 0, 1, 2, 3, 4 and 5. Now let us look at the first case. A is equal to 6q plus 0. We could write this as 2 times 3q. Let us look at the third case. Once again we can take 2 common. So we get 2 times 3q plus 1. Let us look at the fifth case. We can take 2 common and get 2 times 3q plus 2. Now these 3 cases, first, third and fifth, all of them are divisible by 2. Hence they represent even integers. Now the rest of the cases which are not divisible by 2, since they are not even, they have to be odd. So 6q plus 1, 6q plus 3 and 6q plus 5 would represent odd integers. Now we are also talking about positive odd integers. So each of these 3 cases has to be positive or greater than 0. Let us just solve for q and take the smallest value of q. We see that q greater than minus 1 by 6 would give us positive odd integers. So 6q plus 1, 6q plus 3 and 6q plus 5 are positive odd integers when q is greater than minus 1 by 6. Let us look at another problem. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Let us write down our Euclid's division lemma as A is equal to BQ plus R, and we see that we are dealing with 9m here. So we could take B as 9. Now R has to be less than 9. which means that R can take 9 values from 0 till 8. Now that's a lot of cases. Since we are talking about cubes of positive integers, we can take cube on both the sides in all these cases. You could continue this way. However, let us see if there is a shorter way to solve this question. Let us write a Euclid's division lemma, and this time let us take a factor of 9 which when squared or cubed could give us a 9. Let us take b as 3. Now r is going to be less than 3, so we are going to get only 3 cases: 3q plus 0, 3q plus 1 or 3q plus 2. Now let us cube both the sides in all the 3 cases and expand the brackets. Do you notice something interesting? In the first case, we can take a 9 common. So we have a multiple of 9 in the first case. Let us call this multiple of 9 as 9m. Let us look at the second case. We can take a 9 common from the first 3 terms. So we are getting a multiple of 9 plus 1. Let us write that as 9m plus 1. In the third case, we can take a 9 common from the first 3 terms once again. So we have a multiple of 9 plus 8. Let us write that as 9m plus 8. And we have our answer. We have just found out that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Since we are talking about positive integers only, note that m has to be greater than or equal to 0.